far beyond the cacophony of Earth, a third interstellar visitor, designated 3I/Atlas, hurtles toward Mars. The flyby is mere days away, close enough that every space agency should be broadcasting urgent bulletins. Yet mission feeds have fallen eerily silent. Official voices have disappeared. The object's trajectory carves through our planetary plane with unsettling precision, a path no ordinary comet should follow. With its course locked into a corridor tilted just 5 degrees from the solar system's disk and traveling at hyperbolic velocity, it slices through familiar cosmic territory as though guided by deliberate intent. Why have the world's most powerful telescopes gone quiet as 3I/Atlas races toward Mars? What if the truth waiting to be discovered is far more extraordinary and more disturbing than anyone dares to admit? The silence deepens as the encounter draws near. Mars hangs silent in crimson, drifting just 18 million miles from the inbound trajectory of 3I/Atlas, close enough for its orbital satellites to capture every minute detail, if anyone were watching. But the official data streams from Mars Express and the trace gas orbiter remain nearly empty. No press releases, no mission updates. The raw telemetry feeds, typically eager to showcase Martian dust devils or seasonal ice caps, now transmit only routine scientific observations. There's no mention whatsoever of the interstellar visitor threading through their skies. Behind closed doors in mission planning facilities, schedules have been quietly rewritten. Instrument teams discreetly revise observation windows, cramming in high-resolution imaging passes and recalibrating spectrometers to detect water signatures, ice formations, organic compounds, and isotopic anomalies. Yet these modifications slip past public notice entirely. The only breadcrumbs come from buried technical logs, obscure timestamps, and subtle alterations to target lists, while the world's attention remains fixated elsewhere. The flyby window is measured in days, not weeks. At closest approach, 3I/Atlas will streak past Mars at a blistering velocity exceeding 61 kilometers per second, its luminous coma and tail faintly visible to any camera pointed toward it. For perspective, the previous interstellar object, 2I/Borisov, never ventured within 150 million miles of any planet. Now this cosmic wander cuts through space barely 5 degrees above the solar system's plane, threading a corridor that brings it within striking range of Mars, a geometry so remarkably flat and precise that orbital analysts describe it as mission-like. Still, the silence persists. No space agency steps forward to brief the public. The usual chorus of mission scientists, so quick to trumpet discoveries or sound alarms about potential hazards, has gone conspicuously quiet. Even the amateur astronomy networks, those tireless camera-wielding observers who once flooded Discord channels and Telegram groups with every new cometary discovery, find themselves starved for meaningful updates. The encounter looms just days away, and the only certainty is this: the world's best-positioned observers are saying almost nothing. A troubling question lingers in the vacuum. In a solar system built on a foundation of open science and data sharing, what does it mean when the closest witnesses deliberately choose silence? On a quiet southern hemisphere night, the Atlas Survey Facility in Chile flagged an unusual object in its automated scanning routine, a faint, rapidly moving point of light that matched no known solar system trajectory. Within hours, the alert rippled across global networks of orbit analysts. By dawn, the Minor Planet Center had logged the first astrometric measurements, and the hunt for earlier sightings began in earnest. Deep in the digital archives of the Zwicky Transit Facility, researchers unearthed a handful of frames from June 14th showing the identical streak, hiding in plain sight for weeks before its official discovery. Each additional data point refined the orbital solution, and the emerging picture told a story that left little room for ambiguity. This was an authentic visitor from interstellar space. The orbital calculations came together within days. Eccentricity greater than 1, definitively hyperbolic. Excess velocity clocked at 58 kilometers per second inbound. But it was the inclination that truly stood out, just under 5 degrees from the ecliptic plane. Most interstellar objects slash through the solar system at steep, dramatic angles. 3I/Atlas was fundamentally different. Its path hugged the plane of the planets with remarkable fidelity, Tracing a corridor so flat that projected trajectory models showed it would thread to the inner solar system with almost surgical precision. Mars, Earth, Venus, and Jupiter would each lie within a narrow approach corridor, as if the object were following a route meticulously charted by mission planners. For orbital dynamicists, this wasn't merely rare, it was virtually unprecedented. Computer simulations demonstrated that among thousands of randomized interstellar entry scenarios, only a tiny fraction would produce such a coplanar, multi-planet sequence. The Atlas team, led by veteran survey astronomers, transferred their data to orbital modeling specialists and statistical analysts. Each team ran Monte Carlo ensembles, propagating the solution both backward and forward across millions of years. The conclusions were unambiguous. No previous solar system binding, no plausible Oort cloud origin. 3I/Atlas had entered from the galactic field, gravitationally unbound to our sun, traveling on a trajectory that would never return. The probability of this corridor-like path, calculated at less than 1 in 500 for known interstellar populations, added significant weight to every subsequent analysis. For the scientific community, the implications were crystal clear. An interstellar object, confirmed by both archival evidence and real-time observations, was about to sweep through the heart of our solar system. Its low-inclination hyperbolic orbit set the stage for everything that followed: a close Martian flyby, a series of planetary encounters, and a mounting sense that this was no ordinary comet. The facts were established. The questions were only beginning. At 6.4 astronomical units from the Sun, far beyond the frost line where water ice typically remains dormant, 3I/Atlas suddenly flared to life. That initial spike in brightness, flagged by Southern Hemisphere photometry teams, violated every conventional rule in the Comet Handbook. Water ice shouldn't sublimate at such distances. Yet the light curve surge dimmed, then surged again in a pattern resembling less a steady outgassing process and more an organic heartbeat. Episodic bursts, each lasting hours to days, gave the comet an almost breathing rhythm. The photometric data was irrefutable. Amateur and professional observers, connected through Discord servers and late-night Slack channels, watched the magnitude leap by half a point, fade away, then spike again. No ordinary comet pulses with this kind of regularity. The dust dynamics presented another confounding puzzle. High-resolution imaging from Chilean and South African observatories revealed tail segments curving sunward, directly against the expected flow of solar wind pressure. Standard models predict lightweight, fast-moving dust particles streaming away from the sun, forming the classic anti-solar tail structure. Here, the tail was kinked and segmented, with dense clumps lagging behind and occasionally bending forward toward the sun itself. Spectral analysis revealed a dominance of heavier, slower-moving grains, particles that should have either settled quickly back to the nucleus or failed to achieve escape velocity entirely. The tail's geometry, meticulously mapped by photometric analysts, defied straightforward explanations. Some researchers suspected magnetic field effects. Others pointed to volatile pockets, venting in directional jets. No consensus emerged. The light curve, when plotted across weeks of observations, refused to smooth into predictable patterns. Instead, it flickered continuously. Each burst revealed fresh outflows of gas and dust. Each lull suggested either a pause in activity or perhaps a seal temporarily forming over an active vent. The amplitude and timing of these pulses matched neither solar rotation cycles nor any recognized periodic driver. The object appeared to respond to internal triggers rather than external heating. For observers, this translated into sleepless nights chasing unpredictable outbursts and constantly recalibrating equipment to capture the next surge. For theoretical astrophysicists, it meant fundamentally revisiting models of interstellar ice chemistry and thermal stress dynamics. By the time 3I/Atlas reached Jupiter's orbital distance, the dust-to-gas ratio had already skewed far outside normal parameters. Mass estimates derived from coma brightness suggested more material was leaving the nucleus than its estimated size could reasonably account for. Some teams argue for a larger, more volatile-rich core hidden within the dust shroud. Others speculated about ongoing fragmentation or subsurface caverns driving the excess outflow. The only certainty was that standard cometary physics couldn't adequately explain the observations. Professional photometry campaigns intensified, shifting from routine survey operations to high-cadence, multi-band monitoring protocols. Instruments specifically tuned to detect water vapor, carbon monoxide, and organic signatures worked around the clock. Observers logged every brightness fluctuation, every tail anomaly, feeding a growing conviction that 3i/Atlas was far more than just another icy wander from the depths of space. The object's off-script behavior from day one demanded new analytical tools, fresh perspectives, and a willingness to follow the data wherever it led, no matter how unsettling the implications. Every major telescope with a viable line of sight to 3i/Atlas is now operating under heightened alert status, though few acknowledge this publicly. At the European Space Operations Center, Mars Express Flight Controllers have discreetly inserted new coordinates into the week's observation schedule. The trace gas orbiter spectrometers, originally tuned for detecting methane and water vapor in the Martian atmosphere, have been quietly redirected to scan the comet's coma for organic molecules and rare isotopic signatures. Each adjustment gets logged in technical bulletins, never in press releases. The modifications are subtle. An extra imaging pass inserted here, a shifted observation window there. But collectively, they constitute a coordinated campaign built for both speed and secrecy. Halfway across the solar system, the James Webb Space Telescope has carved out precious observation hours from its intensely competitive schedule. During the March through September cycle, a fast-track proposal pushed JWST's NIR spec and MIRI instruments into action, searching for molecular fingerprints of pristine materials, organic silicates, and carbon monoxide preserves as the comet's journey through interstellar space. Reviewer notes, visible only in summary form, describe the observing opportunity as unprecedented. Yet the final time allocation comes with an ominous caveat. The blackout window approaches, and even JWST's massive sunshield cannot bend physics to observe the comet during solar conjunction. Hubble's directors have authorized an extended series of high-cadence imaging runs, focusing on the brilliant halo of dust and gas enveloping the nucleus. Early results reveal a troubling inconsistency. The massive ejected material, inferred from the coma's brightness, far exceeds what the estimated nucleus size can physically explain. If the core measures less than 6 kilometers across, as direct imaging suggests, then the rate of outflow must be driven by mechanisms beyond simple solar heating. Some research teams propose hidden volatile reservoirs or active fragmentation. Others urge caution, pointing to substantial error margins that inevitably plague cometary science at these distances. Outside official institutional channels, a sprawling global network of amateur astronomers has become the backbone of continuous monitoring efforts. In South Africa, Chile, and Australia, coordinated teams race against sunrise to log each outburst event. Discord servers and Telegram groups illuminate with raw photometry data, spectral snapshots, and time-stamped magnitude measurements. Rivalries occasionally flare over calibration methodologies and equipment access, but the data flow remains relentless. When the coma flickers unexpectedly or the tail geometry shifts, amateur observers are frequently the first to detect the change, sometimes hours before professional alert systems catch up. As the blackout window draws closer, every single observation assumes critical importance. Mars orbiters will soon become the only functional eyes with an unobstructed view. Hubble and JWST must stand down, their solar avoidance protocols locking them out of the most crucial phase. For a brief but vital span, the success of the entire observing campaign rests on a handful of spacecraft and the determination of a scattered international community, each watching vigilantly for signs that this visitor represents something far more significant than just another comet. The clock ticks relentlessly forward. The data stream becomes a lifeline. In the weeks preceding perihelion, the official silence becomes palpably heavier. The steady stream of preprints dries up entirely. Conference sessions close their doors to outside observers. Technical notes that were once routinely shared now carry stamps reading operational security and internal review only. Astronomers who previously traded casual Slack messages about filter choices and exposure times now communicate in careful coded language or fall silent altogether. A handful of leaks surface briefly. Fragments from mission chat logs. a redacted email chain bearing the subject line, "Data embargo until further notice." Even the usually abundant flow of raw imaging data from Mars Express slows to a barely perceptible trickle. The data undoubtedly exists, but access is restricted, sometimes for days at a stretch. Behind these quiet institutional walls, frustration simmers. Avi Loeb and his circle of intercept mission advocates push hard for a last-minute spacecraft flyby. The Juno probe, they argue, could be repurposed for a close pass. The response comes swiftly and definitively. Not feasible. Budget constraints are cited. Risk to primary science objectives is invoked. In one leaked Slack exchange, a project manager writes bluntly, "Not a chance." Mission priorities are set. No Delta V to spare. The proposal dies in committee, never reaching public debate or serious consideration. Meanwhile, whispers proliferate through amateur astronomy networks. A Slack channel leak hints at an unexplained technical anomaly, but the specific details are scrubbed before spreading to wider channels. For every rumor that emerges, a counter-rumor appears. Data are being withheld for coordinated peer review or embargoed to prevent premature misinterpretation by the media. The blackout window approaches inexorably, carried with a pervasive sense that the most valuable data may remain locked behind closed institutional doors indefinitely. For now, the corridors of planetary science remain quiet, far too quiet for comfort. Late September 2025. The countdown to perihelion accelerates, but for Earth-based astronomers, the observing window is about to slam shut completely. As 3I/Atlas closes on the Sun, its apparent angular separation from our star drops below 15 degrees, lost entirely in the overwhelming glare of daylight. Hubble and the James Webb Space Telescope, bound by strict solar avoidance protocols to protect their sensitive instruments, enter forced operational downtime. Their observation logs, so recently filled with time-stamped entries and urgent calibration notes, now sit blank and silent. For nearly 2 weeks, from October 29th to November 10th, humanity's most sophisticated telescopes are effectively blind to the interstellar visitor during its most thermally active phase. Mars, trailing just 18 million miles behind in its orbit, becomes a sole vantage point with an unobstructed line of sight. Mars Express and the Trace Gas Orbiter, spacecraft never originally designed for precision comet tracking, squeeze whatever observations their instruments can physically manage. Their flight controllers, working in the shadow of institutional silence, rotate spectrometers to new targets, retask imaging sequences, and push compressed data packets through the narrow communication windows before solar radio interference disrupts the telemetry link entirely. Every kilobyte of transmitted data counts. The fate of the entire observing campaign now hinges on the operational resilience of these aging orbiters and the technical ingenuity of their ground teams. Meanwhile, at the very fringes of the Sun's overwhelming glare, the SOHO and Stereo spacecraft stand ready at their posts. Their coronagraphs, specifically designed to block direct sunlight and reveal the faintest wisps of coronal plasma, may catch fleeting glimpses of 3I/Atlas as it skirts the edge of their respective fields of view. But these are indirect observations at best, sensitive primarily to brightness changes rather than the detailed molecular fingerprints or dust grain velocity distributions that drove the early phase of the campaign. The once flooding data stream narrows to barely a trickle. The blackout is total and absolute. For the first time since discovery, the story of 3I/Atlas continues to unfold beyond the reach of Earth's most powerful instruments, and the world is left waiting anxiously for whatever comes next. For months, scientific debate has circled obsessively around a single stubborn question: exactly how large is the nucleus of 3I/Atlas? Early imaging from Hubble and JWST placed an upper limit of under 6 kilometers for the nucleus diameter. But as the comet approached Mars, the estimates kept climbing upward. Some photometric models, driven by the sheer volume of dust continuously pouring from the coma, now argue for a core potentially up to 10 kilometers across. If this proves accurate, it would make 3I/Atlas a genuine behemoth among confirmed interstellar visitors, and the implications cascade through every theoretical scenario under consideration. Scenario modelers race to map the possible final outcomes. 3 distinct fates dominate the technical discussions. Fragmentation would scatter debris along the orbital path, with each fragment offering a unique window into the comet's internal structure and composition. A dramatic flare, an explosive surge of gas and dust, could signal catastrophic structural collapse or a volatile rich core finally releasing its contents in a single violent outburst. Survival, however, would raise the most provocative questions of all. If 3I/Atlas passes through perihelion completely intact, with anomalous low inclination, fly-by-like trajectory undisturbed, theoretical astrophysicists will face the challenge of explaining not merely its structural strength, but its seemingly purposeful path, whether natural or otherwise. Mainstream research teams lean heavily toward the volatile-rich interstellar comet hypothesis, attributing its oddities to deeply buried ices and unfamiliar chemical compositions forged in alien stellar environments. Yet a vocal minority keeps the mission profile hypothesis alive in discussions, persistently pointing to the corridor trajectory and rhythmic episodic outbursts as evidence of something more deliberate. For now, the nucleus remains concealed behind solar glare and layers of speculation. The final act awaits in the solar fire. Despite months of intense international scrutiny, fundamental questions persist. What triggers its rhythmic, almost biological activity pattern? What accounts for the nature of its unusually dense dust grains? Why do its estimated mass and apparent cometary size diverge so dramatically from all established theoretical models? As Earth-based observations pause for solar conjunction, only the Mars orbiters and solar monitoring observatories maintain partial coverage of the encounter. The accumulated evidence leaves one conclusion beyond dispute. 3I/Atlas has fundamentally challenged standard cometary science and exposed profound gaps in how major institutions communicate extraordinary observational data to the public and scientific community. What transpired at perihelion and what this enigmatic object truly represents remains a matter for future archives and future generations to resolve. 43 hours after perihelion, 3I/Atlas streaked past Mars at its closest approach, a mere 12 million miles, closer than any interstellar object had ever come to another planet in recorded history. In the control room at the European Space Operations Center, the atmosphere was electric with tension. Engineers hunched over their stations, watching telemetry streams from Mars Express and the Trace Gas Orbiter with an intensity that bordered on obsession. For the first time in weeks, data was flowing freely, at least to those with clearance to see it. What they witnessed defied every expectation. The comet's coma, that vast cloud of gas and dust surrounding the nucleus, had transformed. Instead of the expected chaotic expansion from solar heating, the emission showed structure, geometric patterns in the dust distribution that appeared almost crystalline. The Trace Gas Orbiter spectrometers detected something that sent shock waves through the analysis team. Deuterium ratios completely inconsistent with any known solar system object, and organic molecules of staggering complexity. Prebiotic compounds that shouldn't exist in such abundance on a frozen chunk of interstellar ice. But it was the imaging data that truly shattered the consensus. In a series of high-resolution infrared frames captured during a 6-hour window, the nucleus itself became briefly visible through gaps in the coma. The shape was wrong. Not the expected irregular potato-like form of a typical comet, but something with unsettling geometric regularity. One analyst, working the night shift in Darmstadt, later described it in a leaked message as too smooth, too symmetric, like looking at machine-turned metal through a sandstorm. The data was immediately classified under a protocol rarely invoked outside of national security contexts. Within hours, the raw feeds were pulled from public-facing servers. The handful of amateur astronomers who had managed to observe the Mars encounter from Southern Hemisphere observatories reported their own anomalies. Unexpected brightness variations that pulsed with mechanical precision, and a dust trail that seemed to narrow rather than expand as it should. November 3rd, 2025, 3:47 Universal Time Coordinated. A radio astronomer at the Parkes Observatory in Australia, conducting routine monitoring of Mars orbiters during their close approach observations, detected something that shouldn't have been there. A narrow-band radio emission, lasting exactly 42 seconds, emanating not from the Mars spacecraft, but from the region of space where 3I/Atlas had just passed. The frequency was 1,420 megahertz, the hydrogen line, the most fundamental frequency in the universe. and the one that every SETI researcher knows by heart. The signal itself was modulated in a pattern that carried information, though decoding it would prove impossible with a single observation. The astronomer, her hand shaking, immediately called her supervisor. By dawn, the detection had been shared with a small circle of researchers sworn to secrecy. 3 other facilities confirmed they had seen it too in their archival data: the Allen Telescope Array, the Green Bank Observatory, and a private installation in South Africa. Each had captured fragments of the transmission, their collective recordings painting a picture of something deliberately broadcasting as it swept past Mars. The global radio astronomy community split immediately into 3 camps. The skeptics argue for instrumental artifacts or interference from Earth-based transmitters reflecting off the comet's plasma environment. The cautious majority pushed for more data, more observations, refusing to jump to conclusions. And a small but growing faction, including several senior researchers, began privately using a word that had previously been confined to fringe speculation: artificial. By November 8th, as JWST and Hubble emerged from their blackout periods and reacquired the comet, the verdict was clear. 3I/Atlas had survived perihelion completely intact. No fragmentation. No catastrophic outgassing. The nucleus, whatever its true nature, had endured the solar furnace at just 0.65 astronomical units, closer to the Sun than Venus. But something had changed. Orbital analysts began noticing anomalies in the trajectory updates. The comet was accelerating, not just from the expected rocket effect of outgassing, but with a delta-V component that couldn't be fully explained by standard cometary physics. The thrust vector didn't align perfectly with the Sun-comet line as it should. There was a lateral component, small but measurable, as if the object were making a minor course correction. Dr. Sarah Chun, an orbital dynamicist at JPL who had been tracking 3I/Atlas since discovery, ran the numbers a dozen times before trusting her results. If this is purely natural outgassing, she wrote in an internal memo that was immediately classified, then it's being vented through ports positioned with impossible precision. The alternative... She didn't finish the sentence. She didn't need to. The trajectory modification, minute as it was, would carry the object within 0.3 astronomical units of Earth during its outbound passage in late November, closer than initially predicted, close enough for detailed observation, but not remotely close enough to pose any danger, close enough to be studied, close enough to study us. As 3I/Atlas approached Earth, the public's silence shattered. A coalition of amateur astronomers, frustrated by months of official opacity, released their compiled observations in a coordinated data dump across multiple platforms. Detailed light curves showing the rhythmic activity, spectroscopic data revealing the anomalous chemistry, timing analyses of the outbursts that correlated with nothing in nature but showed patterns reminiscent of control venting, and most damningly, leaked communications from professional astronomers expressing concerns about institutional suppression of data. The internet erupted. Hashtag 3IAtlas trended globally. Conspiracy theories bloomed like wildflowers after rain, some absurd, others uncomfortably close to the classified truth. The pressure on NASA, ESA, and other space agencies became overwhelming. On November 20th, a hastily arranged press conference brought together representatives from the major space agencies. The statement was carefully crafted, walking a razor's edge between disclosure and containment. 3I/Atlas represents an unprecedented opportunity for scientific study. While its physical and chemical properties differ significantly from previously observed cometary bodies, we have found no conclusive evidence that would require explanation beyond natural astrophysical processes. The object's unusual trajectory, while statistically rare, falls within the bounds of possibility for interstellar objects. Ongoing observations continue, and all data will be made available to the scientific community following standard peer review processes. What they didn't say was far more significant than what they did. As 3I/Atlas made its closest approach to Earth on November 23rd, a comfortable 28 million miles away, telescopes around the world trained their instruments on the visitor. The James Webb Space Telescope captured images of such clarity that they immediately became classified at the highest levels. Whatever those images showed, they never reached public databases. Amateur astronomers, using nothing more than backyard telescopes and sensitive cameras, captured enough to keep the debate raging. The nucleus, when glimpsed through gaps in the coma, appeared to rotate with a periodicity of exactly 4 hours. Too perfect, too stable for a natural tumbling motion. The dust trails showed bifurcations that suggested directional venting from specific surface features. And through it all, that geometric regularity kept appearing in the data, like a ghost in the machine, impossible to prove yet impossible to ignore. It was a graduate student at MIT, working on her doctoral thesis, analyzing the spectroscopic data, who first noticed a pattern. She had been studying the timing of the emission bursts, searching for any correlation with the comet's rotation or its position relative to the sun. What she found instead made her blood run cold. The bursts, when mapped out over the entire observation period from discovery to Earth flyby, contained structure, not random fluctuations, but variations in intensity and duration that followed a mathematical sequence. Prime numbers. The first 15 prime numbers, encoded in the relative strengths of outgassing events spread across months of observation. She checked her methodology 100 times, certain she was seeing patterns in noise, a victim of paritously applied to data. But the statistical significance held. The probability of this pattern occurring by chance was less than 1 in 10 billion. She presented her findings to her advisor, expecting to be told she had made an error. Instead, he closed his office door, pulled the blinds, and told her something that would haunt her for the rest of her life. "You're the third person to find this. The first 2 were told to bury it. I'm telling you the same thing. For your own sake, this paper cannot be published. Not now, maybe not ever. But secrets have a way of escaping. Within a week, her analysis appeared anonymously on a physics preprint server. Within a day, it had been downloaded 50,000 times before being pulled by the administrators. The file spread through underground channels, copied and recopied across the darknet, and encrypted messaging platforms. The pattern was out there now. The implications were inescapable. Either 3I/Atlas had, through some impossible cosmic coincidence, outgassed in a pattern that mimicked intelligent communication, or something was trying to send a message, something that had crossed a vast gulf between stars to visit our solar system. By early December 2025, 3I/Atlas was accelerating outward, climbing back toward the outer solar system on its hyperbolic trajectory. Within months, it would cross the orbit of Jupiter. Within years, it would leave the sun's influence entirely, returning to the dark between stars from which it had emerged. The official narrative hardened into consensus. An unusual comet, yes, but ultimately explicable through natural processes. The geometric features could be explained by crystalline ice structures. The radio emission was likely plasma interactions with the solar wind. The trajectory anomalies fell within error bars when properly analyzed. The prime number sequence was a statistical artifact, pattern-seeking minds finding order in chaos. But in laboratories and observatories around the world, in encrypted message channels and closed-door meetings, another conversation continued. A conversation about what humanity had witnessed, what it might mean, and what should be done if another visitor arrived. New protocols were quietly established. Detection networks were enhanced. Plans were drawn up for rapid response missions that could actually intercept an object like 3I/Atlas, rather than merely observing from afar. SETI researchers, long relegated to the fringes of astronomy, found their funding requests suddenly approved. Deep space monitoring programs expanded overnight, their true purpose obscure behind bland descriptions of planetary defense initiatives. The data from 3I/Atlas was slowly released over the following months, but always curated, always filtered. The most provocative findings remain buried in classified archives, accessible only to those with the highest clearances and the deepest need to know. Dr. Sarah Chun, the JPL dynamicist who had first noticed the trajectory anomalies, retired unexpectedly in February 2026. Before she left, she updated her personal website with a single cryptic statement. "We are not alone in watching the cosmos. The cosmos, it seems, watches back." 3 months after its Earth flyby, 3I/Atlas crossed the orbit of Mars outbound, now a fading point of light visible only to the most powerful telescopes. Its coma had diminished as it retreated from the sun, the spectacular dust trails collapsing back toward the nucleus. On January 15th, 2026, the Hubble Space Telescope captured one final image of the visitor during a long-exposure deep-field observation. The image showed 3I/Atlas as little more than a faint smudge against the stellar background, already 400 million miles from Earth and receding at 30 kilometers per second. But in that final image, enhanced and processed by automated algorithms, something appeared that no human analyst had specifically looked for: a brief brightening, lasting less than 30 seconds in the exposure sequence. Not an outgassing event. Those were familiar by now. This was different. A flash, directed and focused, aimed precisely back toward the inner solar system, back toward Earth. The astronomer who processed the image sat in silence for a long time, staring at her screen. She could report it, add it to the growing file of anomalies, watch it disappear into classification. Or she could do what her scientific training demanded: follow the data, seek the truth, and share what she found. She began typing her report, knowing that some truths, once released, can never be recalled, knowing that humanity's understanding of its place in the universe was about to undergo a transformation from which there would be no return. In the depths of space, 3I/Atlas continued its lonely journey, carried with its secrets that might take generations to fully understand, if they were ever meant to be understood at all. And somewhere in the vast dark between stars, other objects drifted on their own hyperbolic trajectories, ancient travelers crossing the cosmic ocean, each carrying questions that challenged the very definition of what it meant to be alone in the universe. The story of 3I/Atlas had ended, but the larger story, humanity's story in a universe far stranger and more populated than anyone had dared to imagine, was only beginning.